Okay, so why do we need to do this image subtraction? I mean, let me tell you, this is going to be the most technical part of this day, or possibly what you're doing on this entire school. So why is it so important? And it used to be like this. For example, we're all doing some type of transients here. This is for supernovae. It is example. So what people used to do all the way back to Fritz Zwicky and Edwin Hubble, they took images from one night, then they compare by eye to an image from the next night, for example. So people are still doing this. This is an image by Stu Parker, who runs this backyard observatory supernova search. So it's amateur astronomers who get together and try to find the supernovae. So this is two of his images. And then they just blink them in whatever software they use to view images and try to find something that wasn't there yesterday. I don't know if you can see any difference here. Yeah, so it's actually right there. It's pretty. Yeah, that's right. So if you open up this presentation later on your laptop, you will see it more easily than on this projector. Okay, so this is, I mean, just with an image like this, you could argue, okay, we were able to see the supernova, so why do we need to subtract? And the reason is, I will actually go out from my presentation for this part. So nowadays, our images are not that small anymore. Instead, I want to show you an image from the Zwicky Transient Facility, the P48-inch telescope on Palomar in California. So what you're seeing here, let me zoom out. So this is one exposure of 30 seconds. And this image is showing one CCD quadrant. And we have 64 of these, which we observe 64 of these every 45 seconds. Okay? So let's say you would like to try to blink this image to whatever image you got the next night. It's not going to be very fun for you to try to find a supernova. Okay? So instead, let me zoom it in a bit. So over here you can see this is a galaxy. This is a galaxy. This is a galaxy. Over here you have a galaxy. Over here, tons of stuff in this image. So if we actually do the subtraction, so this is the cutting edge in this field. This is how it should look. You can see that basically everything goes away. And then after this, of course, we use other steps to try to tell us where the supernova actually is. And in this case, there is one, and it was over here. Okay. Doesn't look like much. Let me just link this to the real. If you look very carefully, there is a faint galaxy. If you look in the zoom in, it's easier, much easier to see. Let me zoom in a lot more. All right. To match. Okay, over there you can see a supernova in the outskirts of this tiny galaxy. All right. So this is the reason we absolutely need to do image subtraction in wide field surveys. It's just not feasible to have somebody look at 64 of these every 45 seconds. Okay. Right, so that's one of the things. So transient source detection. But that's not the only thing we use this for. So that's what I just showed. I want to show another example. So this is an image from a smaller telescope of some galaxy. Don't ask me. M82? All right. All right, good. Excellent. Okay, so in this image, there is actually a supernova. Yes, yeah, I will get to that. So this is how it would typically look if you pull it up in DS9 just with the Z scale. There is a supernova here, but you can see the light from the galaxy. It's already close to actually saturating this. This was also for the P48 inch actually. If you adjust the stretch, this is an image before the supernova. This is one after. Okay, so my point with this is the light from the galaxy is very strong. And if you try to do aperture photometry on this, it's not going to work for you. Okay. Or even PSF photometry, it's not going to work for you. Okay, so that's why we need to remove the light from the host and then do your photometry. Okay, this is just showing, put this here. It's some work I did, and this is where my pipeline is actually explained. So you can, if you want to see how these things are explained in a real paper, you can read this one. In that paper, I analyzed the 2 supernova in this galaxy, NGC 5806. The end result should look something like this for you. Very nice, light curves with as little scatter as possible. All right. So you can, after this, you can bring up the presentation and you can go look for this paper. All right. So just one more thing I wanted to say. So for this, this image is observed by the HST, which is a very high resolution, which allows you to do some rather unique science with the help of image subtraction. So what you're seeing here is 2 images of one of these supernova. It's a very, very tiny part of the galaxy, one of these boxes here. So what they did is they observed this supernova before it exploded and several years after it was completely gone. And doing the image subtraction, they were able to find a difference. So this difference tells you something about actually the star that's part of this binary system that happened to produce this supernova. So whatever remains is actually the binary companion. Okay. So this is something you can only do with HST and with a very, very careful image subtraction. Like that. Okay. If you're interested, read that paper. Okay. Yeah, so that's host galaxy subtraction for photometry, and then you might also be interested in doing, for example, the 2D color map of a galaxy with the G-R color, which you can translate to a temperature, for example. If you want to do that, it's very important. Your image is very well matched, which is exactly the same problem we need for image subtraction. Okay, that's just. All right, so moving to the more technical part. This will go pretty quickly because you will be doing these steps later in the Python module. This is a science image and some image to use as the reference. All right, and some of these things we already heard about. For example, this. This is very strongly related to the astrometric solution that people were talking about earlier. So in order to subtract one image from another, your stars will have to be exactly on the same pixel coordinates, otherwise it's going to look like a total mess. All right. So if you have, okay, yeah, let me get back to that. The next thing you're going to have to do is to match the shape of the stars or their point spread functions. All right. The final step is you're going to have to match the 0 points in the images. So, and that just means that the flux of each star should be the same in both your reference and your science frame. What you're doing is just scaling one image by a constant. Okay, and for that part, it's also very useful to use something like PS1 or SDSS, just like Kishalai showed. Is that the procedure will be exactly the same. All right. So one footnote I want to mention here is very common that you will have to improve the background subtraction as part of one of these steps. And this will be in the Python notebook, a fairly sophisticated way to do it actually. But it's very, I mean, the typical workflow for an astronomer doing this is you get some images from some telescope, and then somebody emails you and tells you, could you please do the image subtraction on these images? And they might have done the reduction steps properly, or they might not. And typically the background subtraction is something people really kind of skip over. They just subtract a constant median or something. Okay. So for the image alignment, I wanted to mention a few things. So basically, you just need to know a few stars that are present in both the reference frame and in the science frame. Then you just compare their x and y coordinates, which will be different. In the most simple case, you just have a shift of one image against the other. Well, some maybe 50 pixels in x and 20 in y. That's pretty easy to deal with. As an example here, I just, these are two images from the P48, the P60, I think, actually. And these circles have been placed on the same pixels in both, and you can clearly see the stars are not at the same position. So there is a shift between these. So what you have to do is you have to find out where are actually the same stars. And those are the ones. So from this, it should be fairly clear that one image needs to be shifted down and a little bit to the right. Okay. So how can you make this actually happen? I mean, these are 2D arrays in your Python thing. And this is where actually all those years you were learning about linear algebra actually come to use, fortunately. Okay. Let me show you how that works. So as it turns out, matrix operations are very useful. And there are, you might have seen this, I don't know if you have taken these courses yet or not, but to apply a translation to a coordinate, you just have the unity matrix with two extra terms, these things here, which are just the shift you want to apply in x and y. And that's about it, really. It's really quite beautiful. And if you have also, let's say, a different pixel scale on one image, you just multiply this one with this one. Maybe you have some rotation, then you multiply everything with this one. And it's just matrix operations. All right. And of course, to make this happen in practice, there are modules for Python or whatever programming language you are using. Okay, so that's the image alignment. Next step, PSF matching. Okay, so here I'm showing just the small PSF, maybe that's in the reference, more smoothed one, maybe that's your science image, and you want to achieve actually the same one in both. So how can you do that? It's actually, or the simplest way to do it is actually very straightforward. Okay, so if you consider what a PSF actually is, so it is what happens to a point-like source. When the light from that comes through the atmosphere, the instrument, everything. But the source itself is just creating an infinitely small light source. I mean, that's what a star is, more or less. Okay? So in one image, this has been smoothed to some degree. That is the PSF. That's what happens to that. So, yeah, you can take all the stars in your image, cut them out, stack them on top of each other, do a median combination. That is already quite a good approximation of the PSF. All right. Of course, it's important that you are dealing with stars and not galaxies or whatever. Right. So if you do that for both the reference and the science frame, you know what is happening to a point-like source in both of them. So let's say you want them to be the same. Then you can take the PSF of one image, the science image, convolve it on top of your reference image, and then you do the same again for the reference PSF on top of the science PSF. That just means that the point-like source has been degraded twice, but the end result is exactly the same mathematically. All right. But there are other ways, like was said earlier, you could also use some analytical models to try to model the PSFs, things like that. But yeah, in the notebook, there will be 3 different methods to achieve this. And finally, this step I don't need to talk about really, because Kishalai already told you how to match your aperture photometry against the catalog. You could do it with PSF photometry if you want. It doesn't matter. All right. But the idea is you put your both the science frame and the reference frame on the same same 0 point or same intensity scale, whatever you want to call it. After that, you're basically done, and you can perform an image subtraction. And this is just showing one example with the image we looked at previously. There's a supernova marked by the red one. Most of the other stuff in the frame goes away, except maybe something in the center of the galaxy, and you shouldn't be too afraid if you have some residuals like that, because the center of the galaxy is very likely actually varying a little bit. All right. Moving on to the Python part. All right, yep. Unfortunately, no. But what you will be seeing now it contains all the steps you need to reproduce it. The IDs are the same. Yes, I mean that is mostly taken care of by the PSF matching step. And my code actually uses the simplest possible way, which is the one I told you, where you cross-convolve the PSFs of the science and reference image. There will be, but it's true. It depends on the telescope you have. You have to try this a few times to see how it looks. For example, for Growth India, we do not yet know if it's going to work. We have not tried it. So if you're very ambitious, you could take this image we got last night of the supernova and try to do a subtraction with the same Python notebook. Oh, I don't even remember it. Many different ones. For example, Liverpool telescope against SDSS, it works very well. All our telescopes on Palomar work as well. The 200-inch, the 60-inch, the 48-inch. So it is my feeling that as long as you have, let's say, Sloan filters, the SDSS filters, that are decently matched to the real ones, you're going to be fine. I mean, you will see more residuals than if you had a native reference. But at the level of supernova science, it doesn't matter.
Okay, there are all the questions, that we'll switch to the hands-on part of this module. So everybody could pull up their notebooks. Oh, yeah. So Igor is going to be leading that, and Christopher is going to be assisting. So Igor is the newest postdoctoral member of our family. He just joined Caltech 3 months ago, and immediately took on the responsibility of coordinating this work with just for all of you. So I'm sure all of you have know him and have seen the zillion emails about how he's trying very hard to make all of this work and come together. So we're working with the lecturers, the module writers, and just trying to make all of this work for you. So yeah, hopefully it doesn't require too much of an introduction. Yeah, Igor, special applause for all his efforts actually. One more comment before you start the module is Igor did his PhD at Swinburne University with Professor Jeff Cookie. And by his standards, growth's rapid response follow-up is not rapid enough. So Igor's PhD thesis topic was a deep, wide, fast survey where he was looking for things that change in seconds. So he would commandeer a whole bunch of multi-wavelength telescopes to look at the same piece of sky, to look for fast radio bursts and their counterparts across the electromagnetic spectrum. But he would do that at the time of discovery because the counterpart would just last for seconds. So even if you react to that in minutes, it's too slow for you. So yeah. Anyway, with that,
Thanks.
why not do some minutes subtraction?
Yeah, and now for Sarah, who is continuing the project. So if you have questions about fast transient, ask me or Sarah, and hopefully we'll find more kilonova in the future to make things more exciting. So for this module, first of all, technical problems. There is no end of technical problems we're finding these days. We noticed that some users that use Windows can see the notebooks in the Docker, but cannot see the data, which I can't explain because the method is the same. Thank you. I'm so grateful for that. Everyone else, if possible, please use the Docker in this session because all the software is there. And again, we need to use Extractor, Swarp, and other Astrometric packages. And finally, if you have all this software installed locally, don't launch the notebook from the Anaconda app, but launch it from the terminal by typing Jupyter-notebook and the name of the notebook. So that said, we can start. The correct notebook is this one. Image Subtraction, Growth School V5 is the one that I sent you via email last night. So let's begin. The objective, I hope that by now it's quite clear. Let's look for a supernova in this case. We will have a field where a big galaxy is present, and as a first step beside running the first cell that will allow us to import all the packages, we want to get one image that we consider to be our science image and one image that we consider to be our reference. For example, in this case, is a little bit different than how we usually do it. Usually the reference image is old and the science image is new. But in this case, it went the other way around because first we imaged a supernova when it was bright, and then as the supernova went down, became dimmer, then we can use that image as a reference to discover the supernova in these older images. First of all, let's set the commands. So hopefully things will work. And if you run the first cell, you will be required to insert the path to the data. So you should be quite familiar. It's the path used for the data all the time until now for the school. If you use Docker, simply up data. And if you are outside Docker, this data is probably with the capital D. And if you log in, and if you insert the correct path, you will have a success command. Otherwise, you will be required to repeat the operation until the end of the days. Please raise your hand as soon as you manage to insert the correct path. Okay, I will ask again in a minute so you don't have to stay all the time with the hands up. In the meantime, please go on and set the other path if you have already set the first path for the data. Can you please raise your hand if you have not yet put in the path to the data? Okay, if a tutor maybe can just assist, would be great. Thanks. So, as I said, we will use the Astrometric packages for this module. So we want to assign a command or a full path to the command to Swarp, Source Extractor, and PSFX. If you are in the Docker, it's enough that you leave it the way it is. It's already in. And what this cell is doing is actually calling the command. So if you look at your terminal, as soon as I ran the cell, something happened on the terminal. The command was actually called. And one good flag for things to go well is that a 0 appears. So if a 0 appears, it's not a guarantee that you're successful 100%, but it may be. If you don't get a 0, please set the right command or the right path. I can't come and help you there now. Yes, exactly. So I also wrote it in the comments that in some, depending on the installation that you have of different software, you may have with a capital letter, with 2 capital letters, without capital letters. If you can't find it, just try multiple options. Now, who managed to get up to Extractor and PSFX? Okay, who did not manage to set the path to the data? All good? Perfect. So, Extractor, again a 0, and again, okay, now I lost forever the, okay? So something happened with Extractor now. And finally with PSFX. Okay, so this, as Christopher said, this is probably the most technical module of the school. So don't hesitate to ask for a little bit of help if needed. Who did not make it to this stage? Please raise your hand. 1, 2, 3. Okay, this is actually something that will happen quite a lot during the module. There are some redundant commands of removing temporary files. It's just for safety. They don't affect things at all. Let's just leave them just in case. It shouldn't be necessary. But for example, if you did try to run the module last night at 2 a.m. because you were too eager to know about image subtraction, some images may have created, and this would stop you from progressing today. Sounds a paradox, but that's how it is. So just in case, I set that command. And also, if you want to repeat the operation with the solve notebook, you can do it without being stopped. But please ignore them. You will not have to care too much about it. Now, let's go on. And first of all, you want to identify what your reference image is, what your science image is. And we will go pretty quick here by reading in from the FITS file. This is our template image, our reference. So we just read the image. We calculate some statistical quantities that will help us determining the scale for the plotting. So it's not really anything transcendental. It's simply for the plotting. And we are actually making the plot. Now, something else that we're doing in this step is printing out the dimension of the images. That's quite important later, because when you run SWARP, which is the software that we use for image alignment, it is important that we know the size of the image. Because if you force in SWARP a size of the image that is within the common area of the two images, then the cutout that will result will actually be aligned. If you don't do that, you give too big of a size, the images will not be aligned. So that's why we're printing them out. And in this case, these are CCDs with 1024 pixel by 2048 pixel. Now, the first little task that we require is actually do the same for the science image. So this is for the reference image. Let's do the same for the science image. There are two ways you can complete this notebook so that everyone can just follow at their own pace. In most cases, it's enough to copy what we did before and basically just change a couple of variables. That's one way. I don't recommend that. If you feel confident enough, try to understand even more what's going on and try to go freestyle. Okay? So in this way, we should go all at the same pace, regardless the level of skills. I'll give you 1 minute for this because it's really quick. And I will copy everything. So, if everyone got here, and you don't fail the syntax, you're going to read the feeds file and plot it. Now, question for you all. Give a look to the science image that you plotted and a look to the reference image. What's the difference? They don't look exactly the same, do they? Can anyone think what can going on? One other way you can check this is opening with DS9 from outside Docker. Open the images with DS9. It's much easier to pan through them and understand the different and understand what's going on, because you can quantify each pixel, what's its value. So which image do you think has the best quality? The reference image or the science image? Okay, who says science image to be the best quality? This is reference, this is science. Who says the science image has the best seeing? Who says that the reference image has the best seeing? Okay. Let's do it again. You have to choose. Pick a side. Science image has best seeing or reference image? Who says science image has the best seeing? Who says reference image has best seeing? The correct answer is, thank you for everyone who rose their hand first, the science image has a much better seeing. Which is a sort of unusual situation, because what you really want is maybe have a template that is even better than the science image. It's not a bad thing to have a good science image, don't get me wrong, it's amazing. But to do, for image subtraction's sake, is better if the reference is better. In this way, you can manipulate only the reference and you don't touch your data, your new data. You don't want to do that usually. However, in this specific case, we're forced to do that, and mathematically, as Christopher explained, things should be the same. So, who did not make it to this point? All good? Just one? Get a tutor. All good? Perfect. So, if we go on now, we want to align the images. Okay. So to align them, as I said before, we're going to use one package of the Astrometric software, which is SWARP. So I will not make you create the command yourself, because it requires just a little bit of experience to put the correct keywords. But in practice, what we're telling now the software is the command that we're running. We want to call SWARP with the SWARP path that we set before, the science image as an input, the reference image as well as an input, a configuration file. We say don't subtract the background. SWARP is too smart. SWARP subtracts the background for us, but Christopher wants to show us how we do that. So we say don't do that. Leave the background alone. We want resampling, so the image to be projected on a grid of coordinates that is the same for all the input images. Same grid for the reference and the science image. In this way, we can actually compare them and align them. And we say just to put the images in the out directory. So if you run this command, you can read actually the command here that is printed. And if you find our friend 0, again, it's very likely that things went well. And this is what happened. So SWARP started, read the 2 images, and at the end it says it's all done. In about 3 seconds, which is good, because usually we want to discover transient quick. So we want tools that act in the order of seconds, even less if possible, but not minutes, hours. That's at least not for what I like. I like fast transient. Now, first task. So we do have one science image and one template image that are aligned. I didn't show you earlier, but they were not aligned before. Now you can attempt an image subtraction. Just take the science image minus the reference image. So that's all you have to do. So first we are again opening the images, which we may skip, but in case people come later into this cell, we read them again. And that's all you have to complete. If this is the array corresponding to the science and the template images, if these are the arrays, how do you subtract the data from subtract the data of the reference from the science? You have 30 seconds to do this. And I think you will be quicker than me. Especially because I put a mistake on purpose. Did you all get here? So if you put in the command, which is actually very simple in this case, you have just to say, take the science image aligned, the first extension, and of that just get the data minus the same for the reference image. I added a few lines to plot the result. So this is an image subtraction. This is science image minus reference image. Can you spot the supernova? Can anyone see a supernova, something that is likely a supernova here? Like a bright source that stands out for a gray background? Yes, this one. Unfortunately, if you also have, again, DS9, and in another Windows you want to open the science image, the reference image, and the subtraction, you will see that that's probably coincident with a star. That's probably another type of variable source. It's not our supernova. Our supernova, spoiler alert, is somewhere within here. It's still embedded in the light of the galaxy that we did not manage to get rid of because we didn't do all the other operation that Christopher explained. So let's move on. The background must be subtracted. That's the very first step, because as the light keeps coming in, especially if images are taken with different CCDs or with very different exposure time, at different time of the night, maybe with more moon or less moon, you can have a lot of background problems. And you remove them by using background 2D from the Phototils package.
So why didn't you do background subtraction in that small command?
Because in this way,
Okay, you can try that to enable that at the end and see what happens. The default settings, they will not be variables. That's the reason. It tends to, for an extended galaxy like that, it believes the galaxy is the background, more or less. And they will completely ruin your data. That is one. But it is possible to make it work, but you have to adjust the parameters.
I slightly disagree with the completely ruin. I always do that. But in this way, it's more accurate. So sometimes just getting off the black box of the packages and really understanding what's going on allows you, again, like Christopher did, to find what's not optimal. And fortunately, nowadays with AstroPy, Phototils, and a lot of packages, really we have all the tools that we need to really do things at the highest level. So what we did, again, we make a mask for the sources. We clip them to estimate the background. We use this median background function that I don't know in detail. This is to me a black box, but if you're interested, you can go in the documentation and see a bit better what it does. And finally, we want to remove the background from the image. First, though, we can just make a little plot to see what the background looks like. There it is. So you see the background is not homogeneous throughout the CCD. So that's a very important component. In general, with many more, with other tools that you may want to use, or for example, you can estimate the background as just the median of the value of all pixels of the CCD. That's sometimes a decent approximation, but if you want to do things right, you see that this wouldn't work. If all was the same value, this image would be one color. But this actually, there is a scale, there is a range of values. This means that now we're doing better than what we would do by either estimating the background for the whole CCD or even breaking the CCD down into smaller parts, into smaller boxes, which is another pretty common technique. So let's move on. Let's take both the reference image and the science image, and we remove the background. There is no task for you here. There will be plenty of tasks for you in the PSF matching, don't worry. So in the end, what we do in the last couple of lines, we're simply renaming the image after the background subtraction. So in this way, we're sure that we are continuing with the correct image. Now, the PSF matching is usually fairly tricky. The atmosphere and other factors affect the shape the sources have on your CCD. In a perfect world, or in a world in which your pixel size is huge, every source would be just in one pixel. However, the atmosphere is not a friend of ours in this case if you're observing from the ground, and on top of the PSF of the telescope that you would have also for space-based telescope, you have to add the effects of the atmosphere. So it's very, very likely, let's say it's very unlikely that the PSF of the science image is the same of the PSF of the reference image. That's why we need to do all these operations. And the key to this operation is, first of all, an accurate estimation of what is the shape of the point spread function. And the second step is as a convolution. What sometimes we may like to do is just take the reference image that usually we expect to be very, very good, with good seeing, so with small PSF, and convolve it with the PSF of the science image. And then we can subtract. But again, the equations tells us that if we do manipulate both images, each one with the PSF of the other one, if we make this cross happening, mathematically the result should be better. So we're doing something bad, which is touching our data, our science images. But we're doing something good because we give justice to mathematics. Up to you to see if it's convenient or not. But that's what we're going to test today. So first of all, we will go together in generating a kernel, so a model for the PSF for the science image. So we take the science image and we model its PSF. And then we convolve the reference image with this model of the kernel of the science image. What I will ask you to do later is to do the same operation, but the other way around. Estimate the PSF of the reference image and convolve the science image for it. So, again, discard the first remove possible temporary files, and we run the source extractor command. The reason why we do that is that we want, so if we want to model the shape of the sources of the image, we need first of all to know which sources are there and to get some information about their shape. And source extractor, that's exactly what it does. So source extractor run, and then we use this other software called PSFX that acts on the results that we get from source extractor to generate the PSF. And this is what the result look like. This is the model. So this is the shape of a PSF, which can be in a first order, be approximate with a 3D Gaussian, but seen from above. Now, since we want to perform the convolution, we are using, again, some tools that help us with it. In this case, from SciPy. So we define the kernel, we open it, we eventually convolve the reference image with the kernel of the science image. And the final few lines is just for plotting. And there you go. So the image is a bit smaller than before, because when doing the alignment, we actually cut the edges a little bit, and we smartly selected it to keep including the galaxy. And the image does not look as before. You remember how what the science image used to look before? Like this. You see that the sources are fairly small, let's say. But after the convolution, since the PSF of the reference is very spread out, now also the science image will have a spread out PSF. Now, I think I saw probably 4 people yawning in the last 2 minutes. So it's time for a task. This is probably the largest time we will allow you to perform some operation during the school. So take your time, take 5-10 minutes, and try to do the same steps, but this time estimating the kernel from the reference image, from the science image applied to the reference image. So the opposite of what we did before. Yes, exactly. So in general, having a bad PSF, in principle, shouldn't really reduce your detection limit. But in practice, it's much harder to distinguish a source from the background. Even if the total flux of the source is, of course, the same, it will be much more embedded. So yes, actually, all the tail will become hidden in the noise. So it does. Okay, so for some reason, I can create directories in the current directory from my computer, but most of you can't, even if you're in the Docker. So for whoever is not using Docker, if you have in the notebook directory the directory called out, you should have no problem. Let me know if you do. If you're using the Docker, please do me this favor. Go up, and where you see a directory with /out, Okay, in SWARP, here, if you go up to this cell, align images, this is the SWARP command. Please go all here, and we will do this operation. Instead of out, we will just indicate the local directory. Is that clear? Resample directory will not be out anymore, will be /. And later, when you do names of the aligned images, like everywhere where there is out, just remove out. Just put a dot. Should do, right? So please, everywhere where you see out, just replace it with a dot. Okay, these big errors that you may have sometimes, if the file already exists, so it's not a problem. Okay, if you may receive an error that says file already exists. That's why we added earlier all the remove the temporary files. Mansi, how much time do I have? Okay. busy now. He's blending in. Okay.
I guess another. Why don't you do this? Why don't you measure the background this way and subtract that as part of just do direction?
You can. You can do that. So that's. But the problem is that what happens is when people ask us to do, ask Christopher or me to do image subtraction, in most cases they just don't do it. So you have in hand some images that are already reduced, that are not background subtracted. And actually, even when you, for example, you download the images perfectly processed, I think in case of DCAM, they do their own pipelines to that can be basically reduction as good as it can be. They don't subtract the background. It's just, I don't know why they don't do that. But we just don't give it for granted. But I think you can. Okay, let me finish here and then. This thing that the directory could not be made, just... Okay, has anyone made it to the end of this step? Well done. Like it was hard for me because of this little hiccup, but I'm glad at least some made it. Thank you. Okay. Okay. So since we have 10 minutes left, let's try to go on. And in case you didn't make it here, please try again later. I apologize because I was not aware that it would have been a problem to create a directory, and this messed things up a little bit. So if you made it, great, stay with me. If you didn't make it, please stay with me even more, like look at the screen or pair up with someone close to you who made it at this stage. But let's try to get to the end of the subtraction. So, thank you, Varun. So, in practice, what we did, again, we took the science reference image, we aligned them, we removed the background in case it was not the images that were provided to us by people who observed and reused the data are not perfect. And finally, we matched the PSF so that we can improve the subtraction regardless of the fact that the observing condition could have been different. Once again, the image reduction that Kishali showed us this morning is not always perfect. So what if the astrometric calibration is not perfect? What if I think I'm looking at a point in the sky, but in practice I'm looking at a different point in the sky because my coordinate system is wrong? So the coordinate system is correct, but my images are not well calibrated to it. You can improve the alignment. Of course, if the discrepancy is not too high. And you can do this again using SciPy that provides some tools that, thanks to fast Fourier technique, allow us to improve the alignment in case it was not perfect. So that's what we do now. And I want to quickly move on, because for reason of time, to the normalization of the images. This is very important. So for example, assume that you have a whole night to observe a very interesting target and you stay 6 hours observing it, which never happens, especially in imaging, but for sake of argument. And another night, you just have a second to do that and you really observe for 10 seconds. As you can imagine, if you take the images that was exposed for 6 hours or a stack of images for 6 hours, we'll have an incredible signal to noise. The sources will have a gigantic flux. However, in case you expose very little, the apparent flux of the image is going to be much reduced. So you want to correct for this. So the way we do it, we once again use source extractor. So we measure the flux, not the flux in AB magnitude of the star. These are instrumental magnitudes. So we're correcting again for instrumental effects. We take the instrumental flux of sources in the science image and in the template, in the reference image. If the exposure time is the same, if the conditions are the same, if the world was a perfect place, these two values match. So you don't have to do any rescaling. But we don't live in a perfect world and we may have different amount of time for observing. So what we have is that this scaling factor is usually non-1, okay? A factor that if you multiply by one image by the scaling factor, you should match the other image. So the way we do it, again, we run source extractor, hoping that there are no more problems with the, yes, okay, that there are no more problems with the output directories. And what we do is extractor on the science image, convolved, aligned, background, subtracted. Then again, we do it on the reference image. And now we match catalogs. So matching catalogs is quite a common task for astronomers. There are packages that do it very well in a very efficient way. This is for another lecture. Try to use those packages. Understand how they work, but it's much more efficient if you have million or billion of sources. So what you do, use sky coordinate and the tool called, it's called match catalog, I think, to match two catalog, to match the catalog that we have on the reference image to the sources that we found on the science image. You can use 2D as well. So 3D is also if you want to estimate physical distances between objects also in depth, in the distance far from Earth. So this is a bit using something too powerful for a problem that in principle, let's say it's spherically 2D. It's 2D, simply. So the output of this is what we're printing here are the coordinates of a source in this case, in the reference image, and then the coordinates of the same source in the science image, the way that this package match them. As you see, this is X, this is Y, this is X, this is Y. So the fact that they are very similar tells us, yes, the matching worked well. We are actually looking at the same source. And the value that we're printing next, which is this one, are the fluxes, the flux auto parameter of source extractor. As you see, the difference in flux between reference and science image is huge. If in a perfect world, these two numbers should be the same, but they're not. So what we want to do, we want to find this scaling factor. In this cell, we did something quite useful, which is create an array of the ratio of the fluxes for every source. So there are as many entries in as array as sources, and for each instance of the each element of the array, we fill it with the ratio between the two fluxes. So as many people told us already today, the median is a much more robust statistics than the average, because it allows us, in this context, it allows us to remove all the outliers. So the scale, we can define it numpy.median of our array of the ratio. We call it ratio array. And there you go. In this case, the ratio is a factor larger than 3, so pretty large. And finally, we want to rescale the images and perform the image subtraction. So eventually, we'll perform an image subtraction after all the correction that we did. So whoever made it to this point, I hope it is a few people, let's fill in this line. You have the two images that are called psi convolved and ref convolved. So yeah, that's the fits. I'm wondering how we. Yes, refs image align. Oh no, the convolved like this. With the shift. Thank you very much. And what we did here was to actually calculate the ratio between the flux of the science image over the ratio of the reference image. So in this case, we have to multiply the reference image times the scaling factor.
There's no shift.
No shift? Oh,
Only one shift. But that's one.
okay.
Shift on the side, not on the side.
So here you want shift? Okay, thanks.
You wouldn't shift off. Then you're not aligned anymore.
That's a very good point. Thank you. So data, and this one you want to multiply it times the scale. Okay? So in practice what we did, we took the science image that we convolved and that we shift. And out of it we subtract the reference image convolved, not shifted, because we shifted the reference image on it, and we multiplied it by the scaling factor. And we write this to the subfinal .fits file. And now let's plot the results. Sorry? Okay. So, no, I think it's correct. Well, we will see. You're right. It's not. Too many indices for an array. Great. So it's probably because no, that was correct. Sorry? Which one?
Here you should say fine to make get rid of that.
Okay. So why didn't it work here?
Try it again.
Too many indices for an array. What?
They might be just arrays, so you don't need the zero order of data, nothing like that.
Yeah, that's what I thought.
Not of data either.
Not data.
Yeah, try without.
Okay.
I'm sure.
I did all of this, yes. Wait. Thank you. Okay, finally we made it. Here I created in this plotting cell, basically what I want to do is plot not just the image subtraction, but knowing already where the supernova is, plot a couple of ticks that help us seeing it. So let's start from here. This is the science image. This is where the supernova should be very bright. This is the reference where it's not bright. I can't see any difference. Again, maybe with DS9, if you do proper rescaling, you may see it, but it's very hard. But the image subtraction will actually make the transient stand out, and then we can use against Extractor or other techniques to identify it, then measure it, put it in a nice light curve, and then do science with it. So thank you very much for following. Sorry about the many hiccups, but I hope you got the gist and all the steps for this type of operations. Thanks.